So I think in revenge for, I've argued quite vehemently for something I call computational diversity. And I guess you can blame the PC if this is off the topic of functional programming as you know it. But from my point of view, I'm pleased to represent and probably misrepresent a strange functional programming planet for most people far, far away, which I've come to call vector functional programming just because rebranding sometimes helps. Originally I thought this talk, there was some juggling in the schedule, was going to follow Dean's. So Dean and I last summer, when we were working together, got really fed up with the term big data. So we've agreed to, Dean's trademark copious data. Because in fact, most people who have big data or say they have don't. Normally a talk on vector functional array programming begins and ends with some amazing examples, right? Where there's some exciting program from primes to the game of life presented in a few characters and demoed, and there's usually applause, wow, and a lot of WTF going out of the room. Last summer, Harms, a frequent speaker out of the Chicago area, who's an avid J user, and Chris, who's both a J and K user, we talked and we said, the part of the problem with this is that people just go away kind of, oh yeah, I saw that, sort of curious and interesting. So we kind of changed our approach, so we won't be doing any amazing demos or looking at a lot of code. I'm going to try and talk about why people, in particular, why we've selected array programming or vector programming as the tool of choice. And I'm going to look at fairly quickly at array languages. Fortunately, there's not a lot of them, and they're similar but different. Then I'll talk about a particular dialect of vector functional programming, the one that we use most frequently. In fact, it's one we use pretty much exclusively for the last 5-6 years. And I'll talk a little bit about big data and try and convince you that before you stick everything into JSON and force the rest of the world to have to parse it to do any kind of interesting work, that querying is important. And fortunately, I'm in an audience that actually understands that, basically most operations, functional operations, are essentially can be looked at as a form of query. Link probably being the most graphically known example, but so basically for the last 6 or so years, we've been chartered by a large government organization to help them build tools for analysts. And the tools, the big problem is that they have lots of tools that are good at working at large amounts of batch data. Typically batch is an old term, and usually you associate the word job with it. And so when you hear the word job, I sort of have nightmares. And since I heard that with Hadoop, I was very suspicious. So they have lots of that stuff, and they have lots of computing power. But what they don't have is tools that allow their people to kind of think in their data. So our challenge is exploring a fairly narrow space of people we call thinkers, many of whom don't think of themselves, in fact, deny that they know anything about programming, and definitely don't consider themselves software engineers or anything else. So they know finance, biology, law, lots of other things, and most of them can sort of program in something, script, they are things like that. So they're people who understand that computing is valuable and use it, but they don't really want to be writing programs. And so our job has been basically to provide them interactive tools for thinking in, really interactively in, tens to hundreds of terabytes, which is sort of a small, not medium amount of data, right? Probably more than most companies in Australia have by an order of magnitude. Thinker data sets are by very nature. I know whether you're familiar with the book on the Bad Data book, but basically the quote from it essentially I think says it all. 80% of data science, don't tell anyone, is actually getting the data and cleaning it into a form where you can usably do anything with it. 10% is spent doing data science, and then 10% is trying to figure out how to present it to management so they understand it. The characteristics of real data sets are that they're really quite messy, and they're highly variable. The data sets that we use actually have time in them, and somewhat shockingly, most languages do not have any kind of robust notion of time or time data types, and the databases, if they know about time, they do something really sophisticated, like represent it in characters or something like that. Real data has missing values and out-of-band values. If you have sensors, people step on the sensor when the hikers go through the bush, or they just jam, and so you get out-of-bound values and you get missing data. So to actually work with data, it's nice to have encodings like this. The other issue is that in the world we work in, the data has uncertainty associated with it, which is typically represented with some sort of likelihood function. And so it's very important to be able to compute over all these forms. I mean, we'd like to be able to try and make reliable decisions which actually don't assume that just because you get a certain data set with a certain value, that value is actually can be interpreted as truth or negative. So if you actually look at sort of data languages, a data language is a language that's basically together with the data, as opposed to a language where there's a database or some sort of store and a language that talks to it. Most systems today, other than sort of SQL, in fact, many SQL implementations run a lot of the SQL code in the client as opposed to actually running it in the server itself. Vertica, for example, which is a popular column store for click data, it does store data in columns, and it's actually quite fast with the columns, but you still have to move the data into the client-side memory or into the separate process to actually run your program against it. That turns out to be a little bit of a performance problem. And so, I mean, if you're in computer science, there's a wonderful way to do language design. You start with a few simple and elegant abstractions. In the case of Haskell, of course, pure function execution, and there's only functions all the way down, and everything is typed with type inference, which is a fantastic model, which over the last 20 years is proving to be even more and more powerful, especially in the current decade. I think Haskell's going to really have its impact, and it's very exciting. There's usually a dynamic. By object, I mean the things that are represented, not necessarily an object, right? Functions or whatever. And there's a garbage collector. And the good news is it's very elegant, and if you're really lucky, it has a meta architecture, which can slow it down even more and make it harder to understand. So you have a wonderful model here. The problem is, to get Java fast enough. Now, admittedly, it wasn't a well-designed language. It was an evolved language. There's $2 billion in roughly 10 years of investment by IBM and Oracle alone, and it still can't do closures, tail recursion, or tag bits. It will do closures, but don't trust them if you're a functional programmer, at least for a couple of years. Now, the bottom-up approach is kind of the engineering approach, and I confess that I'm an electrical engineer, and I also didn't have very much time to do this. So one of the nice things about engineering is time is your friend. So basically, you have to get something done quickly, and that constrains your choice. And constraints is the real secret to getting things done in life, from my perspective. So if you want something to be fast, then computers actually only like rectangles. I'm sorry. Pages on disk. Pages in memory, pages in cache, things in registers, the wider the better. So in the end, if you want something to go fast, you have to make it into rectangles. Sorry. Our decision was, well, why don't we just start with everything that's in rectangles? That makes it easier, reduces the semantic distance. Now, the bad news, of course, is that this gives you languages which are not as easy to abstract because you have to convert your problem into rectangles, right? So you're forced to think this way, which is very frustrating. And so our challenge was really trying to find tools that would help normal people basically think in rectangles. And this is very much like trying to program a GPU in a general way. So that led us to vector functional programming. I won't go into this detail, but basically array virtual machines are much faster and much simpler than object virtual machines. And that's one of the reasons. That's the reason we selected them. They're much smaller, they're much faster, they're much easier to they essentially naturally align with a column store. So most of the impedance problems that you have with object models and so on just disappear. Serialization in particular is a joy. Serialization essentially is a count and the vector, right? So, we probably said, well, do you support protocol buffers? And sort of said, well, why would I want to? I already have the world's fastest serialization format, none. So we can slow it down. So that's basically why, and data parallelism is, really trivially implemented, and so you get, and parallelism beyond that requires all the other things, actors or other things. So the question is, of course, well, why would you choose this over? Sorry, that's what I wanted. Over a lazy functional VM. Well, part of it is we were just ignorant in the sense this started 6 years ago in the state, and the other thing is that the techniques for building fast Haskell, and we didn't know about manual and all this great PhD students that were doing all this stuff. So, and we also want a very interactive environment, so we're built on a commercial platform. So we basically went for this, and we went for something with fixed type because that reduces the abstractions. What we find is the more abstraction mechanisms you put in code, the more code bloat you get, and the more overhead. And there's this promise of refactoring, but there's no serious refactoring tools for any decent amount of code. Refactoring is a barber trick promised by people who talk about it, but no one with a serious code base is able to refactor it because there is no tool support for doing that. And I'll dare say that's still true, even for elegant languages like Haskell or for Clojure and so on. There are no tools, serious tools for large amounts of code. The other thing is the libraries are implemented by smart people, not by people who are figuring out how to have a different kind of collection for hash maps or concurrent hash maps every release with bad implementations. One of the problems of building libraries in your own language is that you would get into a conflict between the library and the runtime, because often the runtime needs to know. Like the bad serialization in Java can never do serialization properly because the VM needs to provide you minimal support to support serialization efficiently. You don't need a lot, but you cannot do serialization well just as a library. So there are some issues there. Again, we're looking to efficiently exploit the hardware, and reactive will show us how well that can be done. But in general, hardware doesn't do lazy things all that well. It really likes them to be fairly imperative when it comes there. And the runtime is considerably simpler than a lazy language. I'm sure these problems will be addressed and solved, and people like Ed and Manuel are leading the way, and I look forward to seeing those sorts of things. So way back in time, two characters, particular, Volkov and Iverson, came up with this idea of a programming language, and it was really to describe the hardware. It was essentially a hardware description language for the 370 computers, and it accidentally escaped because it was the only way you could do interactive programming in those days. Your choice was Fortran, COBOL, or APL, and if you were a thinker, there was no way you would have any other choice. And it's a wonderful book that really gives you an idea. Donald McIntyre really talks about the motivation for the hieroglyphics of APL. There is a whole vector system out there in some galaxy far, far away. They do breathe oxygen. We know that. Ken Iverson, there's a wonderful guy called Trenchard Moore who, in a keynote in 1979, brilliantly described everything in the universe as nested arrays. Everything from architecture to biology and so on. And it's a wonderful, wonderful talk. And that spawned languages like NIAL and APL2 and APL+, which, original vector languages only dealt with n-dimensional arrays. This allowed you to nest arrays inside arrays. And in particular, that spawned a number of things. And of course, people sort of said, well, there's some good ideas here, but I only need a subset of them. And you can talk to the people who did S and R, MATLAB, Pinumerics, Octave, and you'll see that they're all inspired from some of these, and more recently Julia, for example, which is a new kind of R. Ken left IBM and decided that he wanted to do a new language which was much more powerful, which he called J, and which is sort of considered to be the CISC vector language. And then Arthur Whitney went off. He actually wrote the interpreter for Ken because Ken was kind of like his adopted father, and Ken didn't understand C, so Arthur wrote the interpreter for J and said, Ken, this is wonderful, but just too complicated for me. So he has the RISC language, the RISC family K. And, there's various other languages based on this. So just to really terrify you, this is exactly what you want on your iPad, right? Nice thing now is I can put an APL keyboard on my iPad. And the good news is I can tweet whole applications to other people, right? The little picture, Touch and Tweet, is actually a project done by some students at the Hasse-Plantzner Institute, basically for remote workers that have handheld devices who are actually working on complicated power systems. And the problem is, on the power system, they're out in the field and they have to ask pretty hard questions like, how much power is flowing through these, which of these things are live, which can I disconnect, and so. And what they do is they talk to someone at the other end who's really good, and they're doing queries and answering questions and shooting them maps. But there's a lot of mistakes with the voiceover and things like that. So basically, they prototype something that actually let you essentially write query programs on your handheld just by moving glyphs. It's really quite effective for their application. Of course, APL is known for, this is John Scholl's very popular video on the game of life. There's been many other things to do this. Sudoku is another favorite. How many characters can you do it? And it's well known in the vector language community that we don't know about KLOCs. We only have characters. How many characters is your program? So these things are very efficient languages, and the badge of honor, you can go to Steve Apter's website, is no stinking loops. So basically, if you're a really good vector programmer, you have no loops in your code, no explicit loops, which is kind of true of most functional programmers, right? You can do everything with maps and function application and so on. And some of you may have heard of patterns popularized by Eric Gamma and so on. But the first paper on patterns is actually a paper by Alan Perlis, who was a giant who died too young in computer science, on lyrical programming. And basically, idioms, most patterns, the patterns that are found in the patterns book are actually just idioms in a reasonable language. Unfortunately, most of them are stolen from functional programming languages that didn't have them, so we had to teach all this goop to object-oriented programmers. But MapReduce, of course, being the most fashionable pattern today. So this has been around for some time. And there's now a movie being made by Catherine Lathwell, whose father was one of the great implementers, called Chasing Men That Stare at Arrays. It's not out yet. And people who look at these, people talk about, one of the challenges has been getting, because we're losing a whole generation of people who thought this way, and there is still a strong community, but the whole way you think in terms of vector programming is not well understood and appreciated. So what Catherine's been trying to do this, but some people talk about lyrical or idiomatic programming. Since they actually move things around in shapes, they think sort of visually, call them shapeshifters or transformers, all sorts of things. Some people think they're just line noise generators, right? Because they look at the characters coming out. But in practice, this is a very different way of thinking. There are a bunch of common features for all vector languages. They're generally applicative and expression-oriented. They're imperative and they have a sign, but most of the computation really is just a data flow transformation. So it's very functional for the most part. And the problem is that when people start, they decide they want to write their whole program in one line. So we generally recommend that people begin by having quite a few little assignments in there and then collapse and fold those back up. Very simple. There's a large library of built-in generalized operations. In most of these languages, there's no local and global scope. For us, that's very important because we want to be able to take queries and push them from a cloud-based system right out to sensors. So it allows us to very easily distribute computations to the site where they need to be. So if the sensor needs to sit there and compute the average with a little bit of power and then get sunburst and actually send up and transmit a packet, it can transmit the average because it can't hold all the data. The programmer here is clearly a consumer. You don't tend to, you need really efficient operations are actually built under the hood in, machine code, probably using C under the misbelief that you actually know what C is doing as a programming language today. The good news is they're all similar, but the bad news is they're all quite different. So programming in one is still a context switch. So it's going to take you at least a month to go from one to the other. In general, since it's functional, you use the usual thing for doing this. There's conditional assignment. The languages like K have a very generalized operation of amend, which is essentially like a scatter-gather operation. So you can basically, position things arbitrarily into an arbitrary structure in a single assignment and do that conditionally. In particular, over and scan are heavily used. In fact, over and scan are actually used in K to implement do and while loops. There is actually no native do and while loops. Everything is done with over and scan, basically, which sort of iterate until a fixed point and then stop. So, and things like recursion and pointer watering, most of the operations there are actually sort of done bottom up recursively. Sort of unnatural style for some people, but an extremely elegant style for some people. I said, no, not for you, Ed. But it's not the way you do it in school typically, so it's not the naive algorithm, right? And so they're very, very fast, but there's only kind of one way to do it, and that's the way you do it. You do it with a scan, and that solves sort of all problems. So, and this gives you a lot of expressive power. I think it's very important. Some people sort of think of this as these are these APL operators, and you're throwing them up in the air and slicing and dicing them, and the solution lands on the table. So, that's the only thing I could get all these array guys to agree on. Yeah, that's the way we think. If you want to learn this, one of the classic problems is people go out and you can download J or download KDB and try either one of them for free. This is not going to be something you learn at home on a weekend. It's an investment. Most people, the way they learn it's very much the way you learn Steam or the Little Lisper. And essentially you practice a lot of exercises. So the first thing you learn is how to do collection programming, I would say. And so you become comfortable with the idioms. And after you've done those for a month or so, then you actually think about writing programs. But until you're comfortable with the idioms, the terminology get in your way. So the first thing is to kind of do your kata, so you still know how to do the moves, right? And know where the keyboard shortcuts are. You don't need many keyboard shortcuts here because just typing the program is the shortest way to type it. So you learn the nouns and verbs and the adverbs, the ways of the idioms of it. You focus on expressions that shape and transform data. And although I'm not a Haskell, haven't had the privilege of programming anything but trivial things in Haskell, this seems to be very much in the same spirit of the Haskell community and the broader functional programming community. you write many small functions. You don't focus on trying to do the smallest one. But unfortunately, it is a disease in an expression-oriented language. As soon as you know how to do this, you go, oh yeah, and it folds back up. So we've been doing some interesting tooling that lets you put comments inside the expressions and slide over the expressions so you can actually comment what's happening at each operation, because you tend to get these very dense codes. We've been looking at things like that. And we built an IDE like light table that exposes the flow of computations and things like that. So we're trying to experiment with how to make expression languages sort of more consumable and most software engineering like, because one of the big criticisms of a lot of this code is you can't read it afterwards. You can't read the Java code either, but that doesn't seem to bother people. I guess when you have to page through it, you say, gee, it must be doing a lot for you. And start with, it's okay to use loops to begin with. You don't feel like you need to spank yourself because you're using a loop or something like that, or you're doing assignments. And as you sort of build up with these kata, then you can start to actually write more interesting programs. And I know some people after Lambda Jam Chicago who did this, and they're actually, have said, I've gotten further with this before. Last time I just quit because I couldn't learn it in 3 hours like every other programming language. The particular language you use is actually called Q, which is a DSL based for finance people, on top of a vector functional language called K. And you can see it has its own vocabulary and list. Some of the words you'll recognize, but some of them are different, like pointer chasing is a scan kind of pattern for doing things. Adverbs are just a way to compose things. Those. Enumerations are a way for dealing with large sets of values of keys, because in general you want characters to go away and encode everything as integers inside, symbols and so on. I don't plan to go through these. This is I know you may know Dennis Schass. He's a professor at NYU, but he writes the Scientific American Puzzles column. And this is basically just a quote from Dennis. Dennis is an avid K user. He doesn't even use Q, right? And sort of only sissies use Q. Well, most normal people use Q because K is just too strange. So the person who did this is probably one of the brightest developers I know, Arthur Whitney, whose father was basically a Harvard roommate of Ken Iverson's. And A+ was his first language, which was really done at Morgan Stanley for dealing with fixed assets. It's been open source since. Then he wrote the interpreter for Ken Iverson's J language. And Roger Huey, who's the principal implementer for J, still testifies that he would not be able to understand J if it weren't for Arthur's initial interpreter, which is still there, even though it was written in an afternoon. It's still the core of the J language. And then Arthur then has built a whole series of languages over the time. And the nice thing about every version of K is it's incompatible with the previous version. Because he actually is one of those few people that actually looks and figures out what should be taken out and changed, and doesn't make a commitment to the past. This works really well if you have a small hostage customer base, which in the case of KDB they do. Basically, if you're doing derivatives and hedge funds, then it's a tool of choice for them. But it's actually an excellent model because he's made some real breakthroughs with each level, and making things backward compatibility would prevent those sorts of things. Now, the nice thing I did convince him with Q is sort of sits a level above this. So the Q level is what most people in finance use, and it's actually stable over time. And he recently has implemented an operating system, KOS and K4. Just as an example, you can see how much more friendly it is to write Sudoku in Q versus in K. It's just a lot bigger. So there's basically it's sort of keyword syntax added to that. And this is sort of a typical Arthur keynote. Well, I don't know what I'm going to talk about, so I think I'll write some code. So he decided he looked at GNU and all these other things and said, gee, everybody who builds an operating system seems to be an editor.
so I should write an editor. And he looked at them, and the smallest one he could find that was useful was about 800 kbytes. I can't remember whether that's with the libraries or without the libraries. It doesn't matter. This is a complete text editor written in K. I think it's about 78 characters, if I recall. So it's an extremely expressive and dense language. It's very simple. I'm getting to the end of my talk, so I'll go on. It basically has noun, verbs, and adverbs, which is a way to basically just compose functions into new ones. And the nice thing is that when you combine it with essentially an SQL dialect, KSQL is much simpler because it does implicit joins and implicit group bys. So that basically halves the size of typical SQL queries right off the bat. And the nice thing is you can put a function in any position. So you have a Turing-complete, very powerful environment. And basically you can easily make DSLs by surfacing new things. I mean, like the select is actually syntactic sugar for that, question mark, table, condition, where, by. That's the actual K code underneath. But, and so you can do very simple sort of things like this. It's got, the basic thing is the complete virtual machine with ODBC, TCP/IP, the web server, and everything like that. It's about 80 kbytes. The source code for the virtual machine and the object code are almost the same size. That's not easy to do, folks. And so it's a complete running platform, and you just bring it up. And that's sort of a very typical, that's a pretty complex, you want to write that VWAP query using most other systems. It's pretty complicated. And the good thing is it executes with really, really pretty good performance. The only thing we need to add is some of that neat stuff that Ed was talking about, and that's where it's going. So let me just wrap up here. This is stolen from Dean. This is word count and scalding. You can see his talk. Here it is in Hive, and that's basically the Q code below, and it's going to be a lot faster. And I won't go in. So the good news is it's really productive very fast. Bad news is it's not really all that well documented. There's 3 errors, domain, type, and range. There isn't a shape system. It'd be nice to have one that would help people reason about more complicated programs. In practice, most of the programs that people write in finance are actually pretty simple. They're much more like scripts. The thing is that after you use it, even our UI guy now is completely ruined because he doesn't understand why we're doing a UI for these people when it's so easy for them just to be able to type Q code in. He says, this is so easy, why do we have this, right? Which is really disgusting because he's a brilliant UI designer. So I'll finish is essentially, the nice thing is that, you can get a lot done in a few lines of code, and so, it really saves you a lot of the trouble of high ceremony languages. The challenges of using dense expression languages from a software engineering point of view is still a challenge, but there are ways to write this code very literally, and we're exploring things that embed documentation, let you query it, let you look visually at the execution path to try and get past that criticism. And we are seeing the spread of this language out of niche things now into others by essentially, underneath it's basically a vector functional, it's basically a scheme interpreter where the lists are represented as vectors. So it's not really that form. Thanks, I'm over my time.